Hello, welcome to this video. We're going to continue the acid-base or Unit 3 Part 2 lecture notes. So in class before break, we talked about a number of different factors that can be used to predict relative acidity of similar molecules. So we talked about electronegativity of the atom bonded to hydrogen. We talked about resonance, we talked about the inductive effect, and the atomic size of the atom bonded to hydrogen. This is the last trend that we will discuss, and this is the effect of hybridization on acidity or basicity. Now notice if you're looking at these three molecules, we can pick any hydrogen as being the most acidic hydrogen because in each of these three molecules, each hydrogen is equivalent. They're bonded to the same atom, same part of the molecule. Also, if we're comparing these three molecules, the hydrogen that we're labeling as the acidic hydrogen is bonded to the same element, carbon, in all cases. But you notice looking at these that these carbons have different hybridizations. So that impacts acidity. And I'll show you the trend first, and then at the end of the table, we'll be able to explain why this is the observed trend. But the pKa of the first molecule, which is ethane, pKa is about 50. So this first part here will have pKa's. Second molecule, ethene, we've got that double bond. The pKa is about 44. So we're 6 units lower pKa. And then ethyne is about 25. So almost 20 pKa units lower. So we have pretty large differences in pKa for these molecules where each hydrogen is bonded to the same atom, all neutral charges, but the only change is the hybridization of that carbon. So as we go left to right in how we have organized the molecules here, remember that lower pKa means more acidic. So more acidic over here for ethyne and less acidic. So that's what I mean by acidity trend, less acidic ethane, more acidic ethyne, and then ethene is somewhere in between. So let's draw conjugate bases to understand this trend. Just like we did for resonance, we'll think about the stability of conjugate bases, and let's remember more stable conjugate base means less stable or stronger acid. So if the conjugate base of these is more stable, then the original acid is more acidic. So if you imagine a base, I'm just going to draw it for one of these molecules, a base taking the hydrogen, and then remember the electrons in that hydrogen to carbon bond break, or that bond breaks and those electrons are now owned by the carbon. So the conjugate base of ethane, losing one hydrogen atom, everything is the same, so I'll draw everything that is not changing first. And then we have a pair of electrons on that carbon. And I'll draw that pair of electrons in an orbital, because that's really where they're existing, is in an orbital. Usually we just draw them on the carbon, but for this part of our notes, we want to draw them in an orbital. Having a pair of electrons makes that carbon negative. While we're here, let's write the hybridization of that carbon atom. That carbon, or both carbons here, but if we focus in on the carbon that lost the hydrogen, it has 4 electron pair domains, 3 are bonds, and 1 is a lone pair. So 4 electron pair domains means hybridization is sp3. Now let's do the same thing for ethene. So imagining a base removes that hydrogen that I highlighted in blue. And remember, it doesn't really matter which hydrogen you choose because they're all equivalent in the structure. That carbon would gain a lone pair. Again, I'm putting that in a orbital, but I'm intentionally making this orbital smaller than the sp3 orbital. The hybridization of carbon in ethene is sp2. And sp2 is a smaller orbital because it has less or fewer p orbitals hybridized, only 2 in sp2, where sp3 has 3 p orbitals hybridized. The sp2 orbital is smaller and closer to the carbon nucleus. So that's going to be key for understanding this acidity trend. For the last molecule, ethine, removing one of the hydrogens. Lone pair, let me make that more obviously an orbital. Is in now an sp orbital. 2 electron pair domains on that carbon means sp orbital. So let's write 3 electron pair domains and 2 electron pair domains. Okay, let's talk more about the size of these orbitals, and we'll describe them as the amount of s character. So in an sp3 orbital, we have an s orbital plus a p orbital plus a p orbital plus a p orbital. And that's how we get sp3. Those are all hybridized. So 1/4 of the orbitals is s, and so we'd say this has 25% s character. For sp2, we have s plus p hybridized. So we have 33% s character because 1/3 of the hybridized orbitals is an s orbital. And then for sp, we have an s orbital and a p orbital, so that's 50% s character. So in each of these molecules, the hybridization, that is the orbital that is present in, that is overlapping with hydrogen orbitals or the other carbon orbital, or this is the orbital that the lone pair electron is occupying. So the hybridization of the carbon atom is also the orbital that non-bonding electrons occupy. Now let's remember an s orbital is spherical shape and p orbitals are dumbbell, and p orbitals can exist further away from the nucleus. So for molecules or atoms with more s character, the non-bonding electrons are closer to the nucleus. So let's look at our examples here. The ethine conjugate base has non-bonding electrons in an sp hybridized orbital. That sp hybridized orbital has more s character than sp2 or sp3. So those non-bonding electrons are closer to the carbon nucleus. The carbon nucleus is positive. Any nucleus is positive. So having the non-bonding electrons closer to the nucleus is a stabilizing effect. So this means now that this is a more stable conjugate base because those electrons are closer to the nucleus, because they're in an sp orbital with more s character. More stable conjugate base means stronger acid. So it's all about orbital size when we're talking about hybridization and the effect of hybridization on acidity and basicity. Okay, let's briefly also talk about pH. So we're moving on to a related but different topic now. So if you need time to digest the previous page, please take a moment to pause the video and do that. We've talked about pKa as being a property of an acid. So let's just write that down as a reminder. pKa is a property of an acid, and remember we determined pKa by adding a certain amount of acid to a certain amount of water and then determining how much conjugate acid and base are present. Okay, so pH, we calculate it in a similar way as pKa, but pKa is a property, pH is a property of a solution. So we're not talking about necessarily a specific acid, just a solution. We calculate, well, let's think about adding first an acid to solution. So looking on the right side here, we have our generic acid HA. Add that to water. If it's acting as an acid, there will be some H3O plus present and some A minus present. The pH of the solution is calculated by taking the negative log of the concentration of H3O plus only. So we're not taking the ratio of products to reactants. We're only looking at the conjugate acid of water, which is H3O plus. So a solution with a higher H3O plus concentration, so more conjugate acid, means, if we're taking the negative log, that means it has a lower pH. Just like low pKa means stronger acid, low pH means more acidic solution. So pH is a property of a solution. It can be experimentally controlled. You can control the pKa, the pH. You can control the pH of a solution by adding more acid that will increase the concentration of H3O plus, which lowers the pH. Or you can add a base like NaOH, and that will in turn raise the pH. So if we're adding acid, which is a proton source, an example is HCl, so a strong acid. This will lower the pH, which means it increases acidity. We have to remember those are inversed. Lowering pH means more acidic. Someone could also add base OH minus, for example, NaOH. This is a strong base. and this would increase the pH or lower the acidity. Okay. So pH can be controlled. Remember, low pH is more acidic. The pH of our stomach acid, human stomach acid, is around 2. That is a low pH. That's acidic. pH of human blood is a little bit above 7, which is very slightly basic. So for this first part of our notes, just remember pH, which is calculated with this equation here, can be experimentally controlled. Low pH means more acidic, high pH means less acidic of the solution. Now, if we have a solution with a certain pH and then add acid to that solution, so we're adding another acid, the pH of a solution is already controlled, and then we're adding acid to that solution. We have 3 possible scenarios of the property of that solution or relative concentration of acid species in solution. So first, let's say that you are adding an acid with a pKa that is equal to the pH of the solution. So pH of the solution equals pKa of the acid. In this scenario, the conjugate base of the acid, HA, conjugate base is A-, and the concentration of that acid, the ratio of these will be equal to 1. So if pH is equal to pKa, you'll have equal amounts of conjugate base and the acid. And again, we're talking about the acid that's added to a water solution. So in this scenario, if pH is equal to pKa, that acid added, HA, exists equally in protonated, which we're talking about HA, or another word is associated. So protonated meaning the proton hydrogen is still bonded to the rest of the acid molecule. Associated meaning the same thing. The hydrogen and the rest of the acid molecule are associated or bonded together. So HA exists equally in protonated and deprotonated. Meaning A-, so conjugate base or dissociated. So concentration of the acid HA, which is associated, and concentration of A-, conjugate base are equal. So we have a ratio of 1. If the pH is greater than the pKa of the acid, so pH of the solution is greater than the pKa, that means that the solution is more basic and the HA that's added is more acidic than the solution. So that means that with the solution being relatively more basic than the acid that is added, the acid will donate its proton, And so the ratio of the conjugate base to the acid that is added will be greater than 1. We will have more conjugate base present because the acid that is added is more acidic than the solution. So in this scenario, the HA exists. We'll say mostly in deprotonated, so A minus, which in other words is dissociated. Form. Then we have one other possible scenario where the pH is less than the pKa. So this means the solution is more acidic and the acid molecule that's added is more basic. So if the acid molecule that's added is more basic than the solution, the pKa is greater than the pH of the solution, the solution is going to act as the acid, and there will be more HA present than A minus. So the ratio of A minus to HA will be less than 1. And the acid HA will exist mostly in protonated. By that we mean the form HA, or in other words, associated. Form. So these are 3 possible scenarios. The pH can be equal to the pKa, or it can be greater, or it can be less than the pKa. So let's do this example. After the example, I'll end the video and then I will briefly review this in class, but if you need to re-watch where this table where I'm explaining these 3 possible scenarios, I know this is a difficult content or a difficult topic to comprehend, but you'll do yourself a favor if you try now to understand it, and then we can confirm your understanding when we are in class. And I do have this note here, so adding to this table. If the pH of the solution is 2 or more units above the acid's pKa, we say the acid is completely I'm going to put that in quotes and I'll explain why. So if the pH is 2 or more units above, that means the acid is more acidic than the solution. So the acid will give away its proton. So we'd say the acid is completely dissociated. So in its A minus form, conjugate base. If the pH is 2 or more units below, then we'd say, let me use a different color. We'd say it is completely associated. So in its HA form, so above would be dissociated, below is associated. But the point of this sentence here is having a pH 2 or more units different from pKa means one form will be an extremely high concentration, and we can often consider it completely dissociated or completely associated rather than having both conjugate acid and conjugate base. But in reality, is never completely. But we can treat it that way. So keep that in mind. But often questions will be stated like what we have here. If ethane thiol is added to H2O solution with a pH of 12, what form will be in higher concentration? So we need to know what ethane thiol is, and we need to know the pKa of ethane thiol. Thiol looks like OH for alcohol, but instead of an oxygen, we have a sulfur. So ethane thiol is 2 carbons bonded to a sulfur atom bonded to a hydrogen. Sulfur is 1 row below oxygen, but in the same column. So this is CH3, CH2, SH. Sulfur has 2 pairs of electrons, just like oxygen would. And the pKa of this molecule is 10.6. Now, one thing you should do here, you should be able to do, is identify the acidic hydrogen in this molecule. We know that hydrogens bonded to carbon are not very acidic. We saw that on the previous page. Hydrogens bonded to other more electronegative atoms are more acidic. So that is the hydrogen bonded to sulfur here that we're talking about. This is the acidic hydrogen. Okay, now we need to consider pKa of 10.6 versus a pH of 12. Well, pH of 12 is greater than, I'll write in values here. pH of 12 is greater than pKa of 10.6. This means that the molecule is more acidic than the solution. So of the 2 forms, I'm going to draw the skeletal structure now, that are in equilibrium, this is the acid or associated. This is the conjugate base or dissociated. All I've done is what we've done for every conjugate base, which is remove the acidic hydrogen and keep the electrons on the atom that was bonded to the hydrogen. With the pKa of the acid being lower than the pH of the solution, the acid molecule, the ethane thiol, is more acidic than the solution, so it will act as the acid and give away its proton. Now the pH and the pKa are within 2 units of each other, so we say both are present in solution. But the conjugate base, the dissociated version, the version without the proton, is in higher concentration. Because SH, ethane thiol, was acidic, acted as an acid, so it produces more conjugate base than the amount of acid ethane thiol that is present. This can also be represented by altering that equilibrium arrow and having a longer arrow towards the side with higher concentration. So towards the conjugate base side, and then shorter arrow in the reverse. All right, I will end our notes here. We'll briefly review this page in class on Tuesday. We'll finish up the next page about equivalence, and then we'll move on to our next unit. Hope you all have a good break, and I'll see you in class on Tuesday.